So welcome to projectile motion. So what's a projectile? We've done equations of motion on objects moving in one direction only. And a projectile is no different to that. For one thing, a projectile could be defined as an object whose only force acting is gravity. Okay, now that's very important and something we're going to come back to. We tend to assume that air resistance is negligible. It makes life a lot easier, and pretty much we're dealing with exactly the same situation as when objects just fall through the air. So think back to your equation of motion questions. But there is one difference. A projectile is when an object is moving in two different directions at the same time. As you can see here, this crazy biker is moving in the y direction, vertically, but he's also displacing in the horizontal direction. Now if we go back to our definition, a projectile is an object where only one force is acting. So this crazy biker, though he is moving in two different directions, he still has weight acting on him. There are two types of projectile motion question, and the first one is called oblique motion. Oblique projectile motion is when the object is initially thrown at an angle, like this, to the horizontal. And this means that the initial velocities, well, we have to do a little bit of calculating when we deal with the initial velocities. So this kind of situation is an oblique projectile. This situation is slightly different. This is what we call horizontal projectile motion. This crazy diver is throwing himself in a horizontal direction to start with. Now this is the second type of projectile motion. This is the horizontal projectile motion. And the maths involved here, in terms of the initial velocity, are a little bit easier to deal with. Let's look at these a bit more closely. Starting with horizontal projection, let's look at what's happening in terms of the horizontal and the vertical motion. Because as we said a minute ago, projectile motion has a mixture of two. What makes projectile motion different to equations of motion is we're dealing with two separate directions. And in fact, that's how we deal with projectile motion questions. We split up the moving object into only its horizontal and only its vertical. And you treat those two completely separately. Now, how do we do this? Or why do we do this, better still? Because the forces acting on an object that's moving in this way are completely different, horizontally and vertically. Vertically, the motion shows uniform acceleration because there is weight acting. There is a single force acting on this frog. I don't know why it's a frog, but there's a single force that's acting, and that is gravity or weight. That weight is pulling it down by a constant value, which means that it accelerates. An object moving under projectile motion would be accelerating vertically, but horizontally there is no force. Remember, air resistance is discounted in these questions. So this means that horizontally the motion remains constant. There is no acceleration. So vertically we have an object accelerating. Horizontally, we have constant motion. The best way to look into this is using flash photography. What we can see in these two photos, or this one in particular, is a comparison between a ball falling under uniform linear motion in one direction, your typical equation of motion question, and a ball, a yellow ball, which is projected horizontally. It's interesting, but both of them fall at the same rate. You can see quite clearly that vertically there is an acceleration. The displacement is increasing by the same amount. So one fraction of a second later, you can see the increments in displacement for both of them. And these increments in displacement are exactly the same in the vertical direction. So it doesn't matter that this ball is moving that way. It's falling at the same rate as a ball that's falling this way. And I'll dig out some videos that actually show you this in motion, just in case you don't believe it. But horizontally, you can see how in this, interestingly enough, a ball going up and down, regardless of the fact that it's decelerating vertically and then accelerating again on the way down. Horizontally, there is no acceleration, so the displacement in each fraction of a second is exactly the same. The vertical motion has zero influence on the horizontal. So let's summarize this information. When dealing with horizontal and vertical motion, it's important to consider the following. In horizontal motion, the velocity remains constant. That means that acceleration is zero. We can go back to using speed equals distance times time, because if we look back to this equation of motion, then we can see that with no acceleration, we can disregard this side of the equation, and we're left with the old speed equals distance over time. In vertical motion, we have a uniform acceleration. Its value is 9.81. Need to squeeze that in. And we use equations of motion to solve for anything else. So these translate into some assumptions that we can make mathematically. We're going to start with horizontal projection. For horizontal projection, our speed can be equal to distance over time. Our acceleration is zero, and our horizontal speed is the initial speed of the object. And that's usually given, or you have to calculate it. It will be u, and we'll put a little sub-letter there, horizontal. For vertical motion, we have some assumptions that we can make quite easily. That acceleration is 9.81, and that our initial vertical velocity, that is the component of the vertical motion, is equal to 0. Now this only happens when we are dealing with questions that are horizontal projection. Our initial vertical velocity would be 0. Now, as an added complication, the two velocities in the end, the horizontal and the vertical, do actually combine to give you a final velocity. An object that lands at an angle will have a combination of both velocities as its magnitude. So how do we find that final velocity magnitude? Well, we're just dealing with vector addition. We are adding the vertical velocity to the horizontal. And that will give us the resultant value. Now, you would never be asked to draw that to scale, but you can use simply Pythagoras to work it out. The square of the horizontal plus the square of the vertical, square root that, the addition of both of those, and you would find your final velocity. But what's also really important is that you find the angle. So when you're asked to work out the final velocity in a projectile motion question, it is vital that you add the size, the magnitude of that velocity vector, plus the angle. So both of those are important. Now we're almost ready to start doing some questions. So let's have a look at this horizontally projected crazy person that's jumping into the sea. What information do we have? Well, the best way to do it is to use a table. And this is just an expansion of what we've done with equations of motion, our little table of data. Horizontally, well, that's either given or you have to work it out. So those two would be separate. And let me just emphasize here, it is really, really important that you separate out all the horizontal information and all the vertical information. And you cannot mix the content of those two sections of the table up. You cannot put information from the vertical into the horizontal or the other way around. And when you use equations of motion, you have to stick to one side of the table. You can't take some values from here and some values from there. That is not allowed. So let's complete this table for what we are already party to. The initial velocity horizontally would be a given, or you would calculate it. Now I'm going to write it as u, h, and I'm going to do this fully, so I'd go back to displacement. Displacement could be written C with a little sub-letter horizontal and S vertical. That's how we would express those unknowns. So initial velocity, what is the initial vertical velocity? Well, because it's horizontal projection, it's 0. Now let's look at the velocity columns. What is the final horizontal velocity? Well, there is no acceleration, so the final horizontal velocity would be the same as the initial horizontal velocity. So that's a very important point. Your final vertical, we're going to call that V. Okay, we don't know. That's something we'd have to work out probably. The acceleration. Our acceleration is 0 in the horizontal, and in the vertical would be 9.81. And the time taken would also be an unknown. But let's have a look at this data more importantly. T is the only piece of information that would be the same on either. So when I said that you couldn't combine information, the exception to that is T. The time it takes for this diver to horizontally displace is going to be equal to the time it takes the diver to vertically displace. So that time is exactly the same. Okay, so let's have a look at the information, because you have to take this with you to when you do an exam question. It won't be given. You have to remember that the horizontal and the vertical are the same, and you have to remember that the acceleration horizontally is 0, and you have to remember that in a horizontally projected question, the initial is 0, and that the acceleration is 9.81. Okay, so let's just go through that again because it's really important. Remember, the horizontal is the same, u initial is the same as final, acceleration is 0, and you must remember that the initial vertical is 0 and the acceleration is 9.81. Okay, and also that time for both would be the same. Okay, so we're going to start this question. What I'd like you to do is we'll read through it together and then stop the video and see how you get on with it. We have a ball bearing rolling across a table with a velocity of 2. When it rolls off the table, right, its initial velocity is horizontal and is equal to 2. So we are dealing with a horizontal projection question. If the table is 1 meters above the floor, how many meters from the base of the table does it hit the ground? So basically it's asking you, what is its vertical displacement? Okay, because as it falls, it will fall like that. So stop the video, complete the table, see how you do in working that out. So let's see if you've completed your table. The horizontal is an unknown, the horizontal displacement is unknown, but the vertical is 1 meter. The initial velocity is 2, and the final horizontal velocity is 2. The acceleration is 0. In the vertical direction, the initial velocity is 0, and the final we've left as an unknown, and our acceleration is 9.81. Our t is unknown at the moment. Right, was your table correct? Now, using only the information, either in one column or the other, see if you can work out the horizontal displacement using equations of motion. Don't worry if you can't, I haven't actually gone through that with you, but if you want a few minutes to try and think about it, then you can stop the video. So how do we solve this question? Well, just like in most projectile questions, it involves a couple of steps. Usually, the vertical information will give you the key to finding your unknown in the horizontal. T, time, is a very useful piece of the jigsaw puzzle because you can use one column to find the time, and then that will prove very valuable for finding it in the second column. In fact, this question is no exception. The way that you work this out is by using the vertical column to find time, and then using that value of time to work out the horizontal. So if we use the equation of motion, s equals ut plus half at squared, we have 9.81 as our acceleration, u is 0, and displacement is 1. Your value for t then should be 0.45 seconds. Now once we have time, we can go back and use the same relationship, but this time using the information in the horizontal column. Okay, so if we now use the horizontal column, horizontal displacement equals u t plus half at squared. But this time, because acceleration is 0, we can cancel out this side, and what we end up with is the horizontal displacement is equal to 2 times 0.45, which is 0.9 meters, which is our answer. So how do we find the net velocity where it hits the ground and that final angle? So we can now put some numbers back into our table. We now have quite a lot of information. We can put our distance and our time in there. So let's have a look at our final velocity. The ball will land like this at an angle. It will have a final vertical component and a final horizontal component. We know what the final horizontal component is. It's equal to 2 meters per second. So now we need to find our final vertical. And we can find that in the simplest way possible. It's u plus at. So we can work that out from 9.81 times 0.45. Okay, so we get a value of 4.4 meters per second. So now we have our second component in the vertical. So what we have to do is find the resultant final velocity. So you remember this was a vector. Like this. So we're going to use Pythagoras to find our final value. Okay, so if we just follow through on this calculation, the square root would give us 23.36. We find the, sorry, not the square root, the square would give us 23.36, and then the square root of that answer would give us the value of the hypotenuse, which is 4.8 meters per second. And how do we find the angle? The angle, we can use any combination from trigonometry. Tan might be the quickest, but it's pretty much up to you. But if we have the vertical velocity over the horizontal, because it's opposite over adjacent, that would give us tan of the angle we want. So 4.4 over 2 equals 2.2, and that's tan of the angle. So we now use tan to the minus 1. I'm stating it in that way because that's how it looks on the calculator, and it will give us our final answer, which should work out to be about 65 degrees. Okay, so I hope you've been able to do some of that on your own, and if not, we will go through plenty of examples in class.